Okay, so on Thursday, we left off talking about hypothesis testing. And we said there are kind of like 4 steps in hypothesis testing. We said first we create our hypotheses, and then we do some preparation. And then we do some calculations. Okay, so I'll pick up right here, and then step 4 was to do the interpretations and conclusions. Okay, so we'll pick up at calculations, and we said the calculations, we are going for something called a p-value. Okay, and so the p-value is the probability of observing our data or something more unusual / extreme if we assume that the null hypothesis is true. Okay, so this is our definition of the p-value. Let me save this. Did everyone get their classes for next quarter? No. Yes, no. It's always, there's always some disappointment and heartbreak. Throughout your entire life, really. But lots of joy too, so, okay. After the rain comes the rainbow. All right, so we've got the p-value, and what we're saying is we say, we basically go along the, we say, for argument's sake, let's assume H0 is true, ... then what is the probability that we end up with our data? Okay, and so when we do a hypothesis test for one proportion, what we end up having is we have a null hypothesis state something like p is equal to 0.5, and our alternative will be something like p is less than 0.5, okay? Of course, this value of 0.5 will depend on the problem, okay? So not necessarily 0.5 in every single problem. We're going to calculate a z-score, okay? The z-score is going to be the difference between what we observed in our sample and the value that appears in our null hypothesis divided by our standard error. So what we're going to have is our standard error is equal to p0 times 1 minus p0 over n. All right, and so let's say we observed 80 games, and we won 32 games. Okay. Does this provide evidence that the game is rigged against us? Okay. What do you feel? You played 80 games. The game says you have a 50% chance of winning. So we should be winning like 40 games. We only won 32. Does it feel like this could be a result of random chance, or does it feel like maybe the game's rigged against us? Huh? Yeah, maybe. Well, let's see what happens, okay? So, you know, we have our hypotheses, our preparation. We basically state that p hat is going to be 32 over 80, so this is 0.4. And our null hypothesis, I'm sorry, not our null hypothesis, our n is 80. So when we do our standard error calculations, I'm going to plug in our values here. What value is my p0? 0.5 times 1 minus 0.5 divided by 80. So I get a standard error of, let me just do some, change the settings on my calculator. Okay, so I got 0.5 times 0.5 divided by 80. And I'm going to take the square root of this. My standard error is 0.0559. Okay, 0.0559. So my p hat is 0.4. My p0 is 0.5. And my standard error is 0.0559. So I'm going to have 0.4 minus 0.5 divided by this value, and I get negative 1.79. So far, so good? Okay, so I'm going to go on to the next slide. I'm going to just copy all of this over, so you know, if you missed it, it's still there. Okay, so our test statistic z is equal to negative 1.79. Oh, I have to slide this over him. Things are cut off. Okay. So our test statistic z is equal to negative 1.79. And then so we're going to look this up in our z table to get our p-value. Okay. How we determine what our p-value depends on the symbol that shows up in our alternative hypothesis. Okay. So whether, you know, to go from a z-score to a p-value, okay, we look at the symbol in the alternative hypothesis. Okay, so if there is a greater than sign, if it's like, you know, p is greater than some number, we take the area to the right. The area to the right of z. If the p is less than something, we take the area to the left of z. Okay? And then lastly, if p is not equal to something, all right, we take the tail area. Tail area is left if z is negative, and right if z is positive. We take the tail area and multiply it by 2. These are our rules to go from a z-score to a p-value. So maybe I'll draw little pictures. So if it's if you have a z, if you have z right here, and you've got a greater than sign, you're going to take the area to the right. If you've got a negative sign, or a less than sign, you're going to take the area to the left. And if you've got a not equal sign, you take the tail area, which is the side away from it, and then you multiply it by 2. Okay, so what would the p-value be associated with negative 1.79, keeping in mind that my alternative hypothesis says less than 0.5? We would use the area to the left of negative 1.75. Okay, so our p-value is the area to the left of z equal to negative 1.79. Okay, so let me pull up my reference table. So we're looking at negative 1.79. I think that's this. Yeah. Negative 1.79, 0.0367. Okay, so our p-value equals 0.0367. Okay, so what this, let's just pause for a second, all right? So this says when you play 80 games, and if the game is fair, you should be winning about 40 games, right? But of course, because of random chance, you might win more than 40 games or you might win fewer than 40 games, okay? If we suspect that the game might be rigged against us, meaning that we have you know, we have less than a 50% chance of winning, then the probability that a fair game would produce 32 wins or less is about 3.5%. Okay? So now we have to make a judgment call. Does 3.5% feel like a large amount or a small amount? Could this be due to random chance? Or do we feel like this is strange enough for me to suspect that the game is rigged? So, okay, I'm going to just copy this onto the next slide, and this is where we make our interpretation, okay? So we get our p-value to be 0.0367. Okay, so part 4 would be interpretation. Okay, so our p-value is 0.0367. So this says, you know, if the game were fair, I would expect to win 50% of the time. Okay? When I played 80 games, I don't know who plays a carnival game 80 times, but let's say I did, okay? When I played 80 times, I only won 40% of the time. Okay? The probability of winning only 40% or fewer games from random chance alone, is only 0.0367. Guess I left my Steam client running. Okay. So now we have to make a choice. Okay, so we have a choice. Is 0.0367 big, or is 0.0367 small? Okay. If we say it's big, then we would say this does not provide evidence that the game is rigged, okay? If we decide 0.0367 is big, we say it does not provide evidence. We say, I guess, our data does not provide evidence that the game is rigged. Okay. On the other hand, if we decide 0.0367 is small, we say our data does provide evidence that the game is rigged. Okay? So our decision of whether it's big or small actually has already been made for us back in step 2 of the problem. Okay? In step 2 of the problem of preparation, we chose a value, the significance level of the test, alpha. Okay? So in step 2, preparation, we chose alpha, our significance level. Okay, so with alpha, our significance level, what did I say? If nobody says anything about what significance level to use, what's the default value of alpha? 5%, right? So so we'll just, assuming, so if alpha is equal to 0.05, how does our p-value compare to alpha? So our p-value is less than alpha, right? So 0.0367 is less than 0.05. So this means what? This means that we've decided that 0.0367 is small, and we say our data provides evidence that the game is rigged. Okay? Our p-value is small. Okay. Does that feel okay? Sure. All right, so on the next slide, I'll kind of just write a summary of the types of conclusions that we would make based on our p-values and stuff. Okay, so basically, if the p-value is less than alpha, this means we will reject the null hypothesis. We accept the alternative, and we say that we have evidence to support the alternative hypothesis, or we have evidence to reject the null hypothesis. Okay. On the other hand, if the p-value is greater than alpha, we will not reject the null hypothesis. Okay. Do not say we accept the null hypothesis. Okay. We cannot accept the alternative. It doesn't mean that we've rejected the alternative, it just means we can't accept it. Okay? And we would say we do not have evidence to reject the null hypothesis. Okay, so these are the conclusions that we would make based on by comparing our p-value to alpha. Okay. So let me let's talk about what exactly alpha is, and we're going to talk about something called type 1 error and type 2 error. Okay, so ideally, if the null hypothesis is false, okay, we conclude to reject the null hypothesis. Okay, and if the null hypothesis is true, we conclude not to reject the null hypothesis. Okay, so these are the ideal situations, okay? But there are two errors inherent to just the process of making decisions on limited data. Okay, and this is these are the errors that exist throughout your life, okay? Whenever you have to make a decision, you don't know if it's the right decision. You don't know if taking a certain action is a good thing or a bad thing, or not taking that action is a good thing or bad thing, okay? You just make a choice and hope for the best. And that's what we got to do, okay? So there's, creatively, we call these type 1 error and type 2 error, okay? So type 1 error, this is the null hypothesis is true, okay, but we incorrectly conclude to reject the null hypothesis. Okay, so that's a type 1 error. So the null hypothesis is true in reality, but for whatever reason, well, because of our data and random sampling, we incorrectly conclude to reject the null hypothesis. So this would be, you know, the game actually is a fair game, but because we happen to have a bad, you know, string of bad luck, we come to the conclusion that the game has been rigged. Okay, that would be type 1 error. Type 2 error would be the null hypothesis is false, okay, but we incorrectly conclude not to reject the null hypothesis. Okay, does this make sense? All right, so now I'm going to give you guys a clicker question. And you know what, it's going to be faster if I type it. So I'm going to type it out here. What's this? Okay, so we're going to say, so imagine a smoke detector, or we'll say, yeah, smoke alarm. So smoke alarm operates on these hypotheses, okay? It says, this situation I'm in, there's either no fire or there is a fire, okay? And let me fire up the clicker machine. Okay, so all right, what is a type 1 error in the context of a smoke alarm? Okay, all right, and so your answer choices are, hang on, I gotta shrink my text here. A will be, there's a fire and the alarm makes noise. B, there is a fire and the alarm makes no noise. There is no fire and this is an alarm makes noise, and D is there is no fire and the alarm makes no noise. So these are your choices. Oh, wait, where's the letter? Okay. The letter D is right there. Okay, so which one is a type 1 error here? Okay, so get your clicks in. We'll ask what's a type 1 error and what's a type 2 error. Okay. So this will be the first question, and then I'm just gonna flip the question around here. Yeah. Huh? What you would conclude? So the smoke, I'm not sure if I fully understand your question. The smoke alarm operates on kind of this premise that, you know, the default state of the smoke alarm is to be, is that there's no fire, right? The default state is to be quiet, all right? And so that's the null hypothesis. It assumes that there is no fire until its sensors detect something that say, hey, there's a fire, okay? And so it's either going to make no noise, or it's going to sound an alarm. So, you know, a type 1 error, you know, what are we doing, okay? All right, do we get our clicks in? Looks like we're missing some people to here today. Okay, so so we got our clicks for type 1 error, and then we'll change this and we'll say what's a type 2 error in the context of a smoke alarm. So this will be the next question. I know they all look, it's like, they're just variants of each other, but they are, you know, significantly different. Okay, so I'm going to go ahead and click stop here. All right, and let's talk about this. So we'll create a quote a snip. Whoops. Okay, so what we have here, so there is a fire and the alarm makes noise. This is a good thing. This is correct operation. Okay, there is a fire and the alarm makes no noise. This is a type 2 error. Okay, this is, we did not reject. No noise would be not rejecting the null hypothesis. When there is a fire, it would be the null hypothesis is false. Okay. There is a fire and the alarm makes noise. That would be, this would be type 1 error. Okay, so the alarm makes noise. This is basically rejecting the null hypothesis. Okay, when we, so there is no fire. You know, our decisions would be to either reject or not reject. So rejecting the null hypothesis would sound an alarm, makes noise, and there is no fire means the null hypothesis is true. Okay, so type 1 error would be kind of a false alarm. And then type 2 error would be, well, I don't know what we call this, a false negative, I guess. False positive and false negative. Okay, and then there is no fire and the alarm makes no sound. This is correct operation. Okay, so let's, question 1 indeed was C, and then question 2 indeed was, whoops, B. Okay. Okay, is that okay? All right, so in this case, which error is worse, type 1 or type 2 error? Type 2 error is worse, right? Type 2 error is worse than type 1 error. Okay? Type 1 error is annoying. Type 2 error is potentially tragic. Okay? So if you're a smoke alarm company and you have to manufacture smoke alarms, would you err on the side of making your things overly sensitive or not sensitive enough? We would rather have people complain that the smoke alarms are overly sensitive, right? Okay, so we prefer to have overly sensitive alarms in the case of a smoke alarm. Okay. So when we can relate this back to our choice of a significance level. Okay, so it turns out that the significance level alpha is equal to the probability of a type 1 error. Okay, so if we say alpha, so if alpha is equal to 5%, when we conduct a hypothesis test, we are basically acknowledging that I might make a type 1 error about 5% of the time. Okay, so we are quote unquote willing to make type 1 error 5% of the time. Okay, and you might say, well, I don't want to make mistakes. I should use alpha 1% or alpha, 1 in 1,000. Well, you can't have it all, okay? So if you decrease alpha, you will be rejecting the null hypothesis less often, which means inherently you are now increasing your risk of a type 2 error. Okay? So by decreasing alpha, you're going to be rejecting the null hypothesis less often, which just means the chance that you haven't rejected the null and that was a mistake now goes up because you're just not rejecting the null as often. Okay, so choosing to decrease alpha increases the probability of type 2 error. Okay, so we assign, so alpha is the probability of a type 1 error. And we give beta probability of type 2 error. Okay, so alpha is the first letter of the Greek alphabet and beta is the second letter of the Greek alphabet, so this is how you can kind of remember. Type 1 error is alpha, type 2 error is beta. Okay, that's actually where we get the word alphabet from alpha and beta. The more you know. So we have beta is the probability of a type 2 error. So the general relationship is, decreasing alpha will increase beta, and on the other hand, increasing alpha will decrease beta. Okay, we give a name to the complement of type 2 error. Okay, so 1 minus beta would be the probability of of not committing type 2 error. So what is not committing a type 2 error? What does that mean? Can you tell that this is a 2? What does it mean not to commit a type 2 error? So let's think about this. A type 2 error was we chose not to reject the null when the null was false. Okay? So not doing that would be to reject the null when the null is false. Okay? So 1 minus beta would be the probability of rejecting the null when the null is false. Okay? Is that a good thing or a bad thing? It's a good thing, right? If the null is false, we want to reject the null. Okay? So probability of rejecting the null when the null is false, this is a good thing. And so we call the probability of this good thing power. Okay, so power is 1 minus beta. Okay. In general, we have choice of alpha. We don't really have choice over beta. Okay, so we can choose alpha. Okay, we can't choose beta. Okay, but we can modify alpha to so beta fits the needs that we want. Okay, so I guess just further extending this, increasing beta will decrease power, and decreasing beta will increase power. Okay, so let's come back here and we'll say in the context of smoke alarms, would we prefer to have a large alpha or small alpha? And I guess your choices will be big alpha better, B will be small alpha better. What? And I don't know. That's really it. Okay, so let me start this up. Somebody clicked an E. Oh, okay, no, they fixed it. Big alpha better or small alpha better? Okay. So alpha is the probability of a type 1 error. Okay, I'm going to go ahead and click stop here. So last few clicks. Okay, and 92% of you are correct. Big alpha is better. Big alpha is better because we have decided that type 1 error is less bad than a type 2 error. Okay. Okay, so this is because a type 2 error is worse than type 1 error. So big alpha is better. Okay? Let me just describe a scenario where maybe type 1 error is worse than type 2 error, okay? So another scenario. Okay, so imagine a criminal trial, okay? In our justice system, we say the defendants are presumed what? Innocent until proven guilty, right? So we go off of the assumption that the defendant is innocent. And the alternative is that the defendant is guilty. Okay? So in our ideal scenario, if the null hypothesis is true, if the defendant is innocent, we acquit the defendant. Okay? Or the jury acquits. And ideally, if the null hypothesis is false, meaning if the defendant is guilty, the jury convicts. Okay, so this is the ideal case. Okay, but because all of the information is not known at all times, juries and judges make mistakes. Okay, so a type 1 error would be rejecting the null when the null is true. So this means type 1 error would be convicting an innocent person. Okay, and then a type 2 error would be acquitting a guilty person. Okay, and these are both mistakes, and we don't want to make either mistake. Okay, we don't want to make either mistake. But if you had to make a mistake, if you had to make more of one mistake than the other, which mistake is worse? Okay. Huh? Depends on the situation. Okay. Huh? Yeah. Well, okay. So at least with the way our justice system is set up, our justice system is set up in a way that says the type 1 error is worse. That convicting an innocent person is worse than acquitting a guilty person. Okay. And maybe there's some debate here, but we say the type 1 error is worse. Okay, so because the type 1 error is worse, we choose to have a small alpha. Small alpha is better. Okay, type 1 error is worse, so we prefer to have a small alpha. Okay, and they actually say this in trials. Okay. They say, they don't say use a small alpha, but they do charge the jury that, if you're going to convict, you want to be sure beyond a reasonable doubt. Okay, so they use the phrase, beyond a reasonable doubt. Okay, so that juries don't convict based on a hunch or just a gut feeling, but beyond a reasonable doubt. Okay, that's it. Have a great weekend. We'll see you guys on Monday. Enjoy the Oscars.
Thank you.